Okay, so in the last lecture you see we got the differential equation that is satisfied by the Weierstrass Phe-function for a torus. Okay, so let me write that differential equation down. So you see, so we have tau in the upper half plane, set of all complex numbers such that imaginary part of z is greater than 0, and corresponding to tau we have the lattice defined by tau, which is the set of all m plus n tau, where m and n are integers. Then we have the torus defined by tau, which is simply the complex plane modulo L tau, and this is going modulo the equivalence relation if given by translation by an element of L tau. Okay, so in other words, two complex numbers are said to be related if one is a translate of the other by an element of L tau, and this is this is the complex torus, associated complex one dimensional torus. Okay, it is a compact Riemann surface of genus 1, right, which is associated to this torus, I mean which is associated to this element of the upper half plane. Okay, and we are, and of course we associated to this tau the Weierstrass Phe-function p tau of z, which is 1 by z squared plus sigma omega in the lattice omega not equal to 0 1 by z minus omega the whole squared minus 1 by omega squared. So this was a Weierstrass Phe-function, and then we showed in the last lecture that this Phe-function satisfies a differential equation now, and that differential equation is just to write it correctly, p tau z, the derivative the whole squared is 4 times p tau z the whole cube minus g2 times p tau of z minus g3, where g2 is summation over omega in the lattice omega not equal to 0 1 by omega power 4, and I think there is a constant which is going to be I guess there is this whole thing into 60. Okay, and g3 is summation over omega in the lattice omega not equal to 0 of 1 by omega power 6 into 140. Okay, these were the constants that we got. Okay, and this was the so I was telling you last time that somehow this differential equation, I mean if you call p of tau as a variable x and p dash of tau as another variable y, then this is the equation y squared equal to 4x cubed minus g2 x minus g3, which is the equation of a cubic. It is a cubic polynomial equation, and that is the first hint of the fact that the torus is actually algebraic. Okay, we will see that later, but for the moment you see the aim of our discussion has been to show that we wanted to show that the set of holomorphic isomorphism classes of tori, namely the set U mod PSL2Z, which we have managed to make into a Riemann surface, okay, the upper half plane modulo the action of the unimodular group PSL2Z, okay, we have managed to make that into a Riemann surface, and we want to show that that is holomorphically isomorphic to the complex plane as a with the natural Riemann surface structure. So you see this, as I was explaining last time, this leads us to find invariants for tori, okay, quantities which depend only on the holomorphic isomorphism class of a torus. So you try to attach to every torus a quantity which depends only on the holomorphic isomorphism class of the torus. But you see this means that you are trying to find a function on the upper half plane which is invariant under PSL2Z, okay, because the orbits of PSL2Z in the upper half plane are precisely the holomorphic isomorphism classes of tori, okay. So the aim is somehow that you want to cook up a function on the upper half plane, okay, which is invariant under the action of PSL2Z, okay, that is what you want. So and I told you that because of this philosophy you are trying to find invariants for tori, and therefore somehow the value of the invariant at a given point tau has got to do with the geometry of the torus that it defines, and then you know we took in the general philosophy that you see the geometry of the torus should be dictated by the functions that it allows, and searching for such functions is what led us to get the Weierstrass Phe-function, okay, and then we got this differential equation, alright. Now the reason we got it is because we can use this to cook up a function on the upper half plane, a complex function on the upper half plane, in fact an analytic function, okay, which will be a kind of invariant. To begin with, what I am going to construct today is what is called as it's called a modular function, alright, and this modular function will finally I want a function which is invariant under the whole group PSL2Z, but for the moment I will begin by constructing a function which is invariant under what is called a congruence mod 2 subgroup of PSL2Z, namely the subgroup of matrices which are congruent to identity when you read the coefficients mod 2, okay. So I will explain that, okay. So to begin with what you do is so this is to recall, but now let us take this differential equation and you know write it in the following form: p prime tau of z the whole squared is equal to, let me write this as well, 4 times p tau of z minus E1 into p tau of z minus E2 into p tau of z minus E3. Let me write it in this form, alright. So in other words you see the I am thinking of the right side as the polynomial 4x cube minus g2x minus g3, okay. So you take 4x cube minus g2x minus g3, okay, this is a polynomial, alright, of degree 3, and it will have 3 roots, alright. So if you write those roots, if you write the factorization in terms of the roots, the factorization will look like this. It will look the leading coefficient into x minus the first root into x minus the second root into x minus the third root. Of course it is true that you see x is p tau, therefore it is obvious that since x depends on tau, your E1, E2, E3 will also depend on tau. You must understand that E1, E2, E3 are also functions of tau, okay. So they will change if you change tau, alright. So and the point is, the key is to find what these what these E1, E2, E3 are. Okay, so to find, you see, we would like to look at when for what values of z this side vanishes. Okay, because on this side I have p tau prime whole squared. If this vanishes, this will vanish only for values of z for which either one of the three vanishes. Okay, so I am just trying to find out for what values of z will p tau of z be equal to 1 of the ei. Okay, and these will be precisely the values of z for which the derivative vanishes because of this differential equation. So this is how I am using this differential equation. Okay, so let me write that down. The values of z for which p tau of z is 1 of the ei are precisely the zeros of p tau prime of z. Okay, these are precisely the zeros of this function which is on the left. All right, now let us try to so I'll first try to tell you that there are 3 easy zeros that you can guess. Okay, so let omega be an element of that lattice. Okay, so then you see if I take p tau of omega minus z, okay, let me calculate p tau of omega minus z. See, this is you see, therefore you know omega is in the lattice, therefore omega is of the form n plus m tau. All right, so I take p tau of omega minus z, and this is, you see, this is p tau of z minus omega. That's because p tau is an even function. All right, the Weierstrass Phe-function is an even function, which you can anyway see by looking at this series expansion. It involves only even powers, right? And you see, since omega is a period, this is also equal to p tau of z. Okay, so now you take the first one, the last one, and differentiate with respect to z. Okay, what you will get is, you will get, if you differentiate the first one, I will get minus p tau prime of omega minus z is equal to p tau prime of z. Okay, and now you see, I suppose I plug in z is equal to omega by 2 in this. Okay, put z is equal to omega by 2. What you will get is, you will get that omega by 2 is a 0. So you will get 2 times p tau prime of omega by 2 is 0. So this implies p tau prime vanishes at omega by 2. Okay, for every omega in the lattice. Okay, so in particular, if you look at the so let me draw this period parallelogram, this fundamental parallelogram, namely the parallelogram formed by the generators of this lattice. So you see, you have 1 here. Okay, and well, you have tau somewhere here. So this is a complex plane, and this is the upper half plane. Okay, and tau is there, and I have this so I have this parallelogram here. This point is 1 plus tau. Okay, and well, the 3 zeros I can immediately, 3 distinct zeros I can immediately spot in the closure of that parallelogram are, of course, half tau by 2 and 1 plus tau by 2. Okay, so I will get a 0. So I will get a 0 here. This will be tau by 2. Okay, and of course I will get a 0 here, which is half, and then I will get a 0 here. This is going to be 1 plus tau by 2. of course you have to be careful that here omega is not 0, okay, omega is not 0 because I cannot put omega equal to 0 here because the derivative at 0 is not defined, okay. So the point I want to make is that you see if you translate this parallelogram a little bit, okay, so that these two zeros are not on the boundary of the parallelogram, then my claim is that these are the only 3 zeros and they are simple zeros for p prime tau, okay. So the claim, so let me draw another parallelogram which is slight shift of this parallelogram so that these two zeros come inside the parallelogram, okay, a translate of this parallelogram. So let me draw it. So it should look something like this. Let me put tau by 2 here, and so that I can so let me draw a parallelogram like this. Okay, and let me write the half here. And here is the translate of this parallelogram. Let me call this parallelogram as O A B C. Let me call this parallelogram as O A B C, and and let me so let me, if I want to integrate along the edges of this parallelogram, okay, as a closed path, then the orientation I take is the counterclockwise orientation. So the orientation is like this, okay. So but the claim is the following. The claim is the only zeros of p prime tau of z in this translate in OA BC are these three, 1 by 2, tau by 2 and 1 plus tau by 2, and these are simple zeros, okay. So this is the claim. The claim is that these are simple zeros, okay. So how does one see that? So the first thing that one needs to use is the so called so you will have to use the argument principle, and you also have to use the residue theorem at the same time, okay. So for that what you do is consider this integral. I integrate over OA BC, which is a closed path, okay, with the orientation the way I have drawn it, okay, and I am going to integrate the function p tau prime the whole prime by p tau prime of z dz, okay. I am going to look at this integral, all right. Now on the one hand you see because p sub tau the phi function is doubly periodic, okay, this function continues to be doubly periodic, function continues to be doubly periodic, and with periods 1 and tau, okay. Therefore if you break this integral into 4 pieces, one along each edge of the parallelogram, then you see the integrals, the contributions for the opposite edges will cancel, okay, that is because of periodicity. So this is equal to 0, which is, so let me write that, which is 0 because the integrand is periodic, has periods 1 and tau, okay. So I'm again and again using this fact that you see the I mean another way of stating this is trying to say that the sum of residues of an elliptic function is always 0, and this is an elliptic function, it is meromorphic and it is periodic with respect to both 1 and tau, okay, and that result also comes in the same way because you integrate over a suitable parallelogram like this, okay, and then you see that the integral automatically becomes 0 because of periodicity. On the other hand, the residue theorem tells that this is 2 pi I into sum of residues of the function at the poles inside this parallelogram, right. So this is on the one hand 0, okay. On the other hand, what is the argument principle? See the argument principle tells you that integral of f prime by f dz will be 2 pi I times number of zeros counted with multiplicities minus number of poles counted with multiplicities, okay. So let us apply that. It is also equal to, by the argument principle, this will be so this integral is already 0, so I will get on the left side I have 0, that is equal to, so number of zeros in OA BC, okay, and when I, of course you know when you take number of zeros you have to count them with multiplicity, you have to count zeros with multiplicities, when you count poles you have to count poles with multiplicities. So it is number of zeros in OA BC counted with multiplicity minus number of poles in OABC counted with multiplicity, but for which function? For the function, so this is for phi prime sub t of z, okay. So here let me write that for phi prime sub t of z, and here also it is for phi prime sub t of z, okay, and it will be this into well 2 pi I, okay. This is the argument principle. Now you see you know p prime tau of z has you know that it has precisely a pole of order 3 at each lattice point, okay, because you see if you recall we have this p prime tau of z is equal to minus 2 sigma omega in the lattice 1 by z minus omega the whole cube, okay. We have this, we get this by differentiating this term by term, which you can do because of uniform convergence, right, and this clearly tells you that at each lattice point you have a pole of order 3, alright. So in this parallelogram, okay, the only pole is at 0, okay, and it has to be counted 3 times. So therefore the number of poles, this is 3, alright, minus and here I will get number of zeros, okay, and the zeros, the only zeros are these 3 and they will occur with some multiplicities. It's no so let me write that, suppose I write n sub n of half as a multiplicity of 0 at half plus n of tau by 2 as multiplicity of the 0 at tau by 2 and n of 1 plus tau by 2 as a multiplicity of the 0 at 1 plus tau by 2, then this is the sum, this is the number of zeros counted with multiplicity, and this into 2 pi I, this is equal to 0. What does it imply? It means that each one has to be at least 1, so but the sum is 3, therefore each one has to be 1. So the moral of the story is it tells you that these are 3 zeros and each of these zeros are simple zeros, plus it also tells you that you cannot have any other zeros, because otherwise this you want this will, because the sum of all the zeros counted with multiplicities has to be equal to 3, okay. So this implies, so that implies this claim, okay. So this implies the claim, okay. So what we have proved is that the zeros of P prime are precisely these, okay. And now the next thing that I want to say is well so where are we? So we are we know that for z equal to half and tau by 2 and 1 plus tau by 2 p tau of z will be either E1 or E2 or E3. So let us put so we can put E1 to be, you know, p tau of half, okay, E2 to be p tau of tau by 2 and E3 to be p sub tau of 1 plus tau by 2, okay, because E1, E2, E3 are precisely the values that p tau has to take in order for the right side to be 0, and that means these have to be zeros of p tau prime, okay, p prime phi prime, okay. So so we do this, so we have managed to find what these for what values you will get zeros on the left side, on the right side, by looking at the zeros on the left side, alright. Now the next thing that I want to tell you is I want to make another statement. I want to make the statement that none of so you see now already what you see here is that there is a dependence on tau, okay. See, this is what we are originally looking for, because we are trying to cook up a function on the upper half plane and tau is varying in the upper half plane. So you see tau is showing up already, alright, but we have to make so first thing is I claim that E1, E2, E3 are all distinct, okay. I claim that E1 can never, no matter what the value of tau is, okay, no matter what the value of tau is, E1 can never equal E2, E2 can never equal E3, E1 can never equal E3, okay. So that is the next claim, alright. So let me write that down, so let me write that down here. Claim E1 is not equal to E2, E2 is not equal to E3 and E1 is not equal to E3 for any tau in the upper half plane, okay. I claim that all these values are different. Even if you fix a tau, okay, then you get 3 values of E1, E2, E3, okay, and these three are 3 distinct values, okay. And how does one prove that? So that involves trying to understand what is called the order of an elliptic function. So let me define this. So you see let me do the following thing. So maybe so let f of z be an elliptic function elliptic function with respect to L of tau. What does it mean? It means that it is a doubly periodic function, okay, which is meromorphic, which is that is it is analytic except for poles, okay, that is it is periodic with periods 1 and tau and is meromorphic. Meromorphic means the only singularities that are allowed are poles, So you take a general elliptic function, okay. This is an elliptic function connected to this lattice, alright. Now of course you know what this means is that you are considering on the complex torus a general meromorphic function, yeah, because a function like this. So what is this? This is a function which is in which goes from C minus the lattice to so in fact I should say C minus set of poles, okay. It goes from C minus set of poles to C, okay. So this is my function f, and if you want you can also consider it as you can extend it to a function f from C to C union infinity, okay. You allow you set the value of f at a pole as infinity, so you can also think of it as a holomorphic map into the Riemann sphere, okay. And the point is that since it is invariant under the lattice, it will go down to this torus. So there is this projection map which is going modulo L tau, that goes to T tau, which is just C mod L tau, okay. And you get therefore you get a map like this. So you get a map like this. So maybe I can call this as f bar, okay, and this diagram congruence, okay. And of course the fact that because this is a locally biholomorphic map, because this is a universal covering, it is a holomorphic universal covering, it is locally biholomorphic, therefore this guy is holomorphic. So in other words, what is f bar? F bar is a holomorphic map from this complex torus into C union infinity, that in other words it is a meromorphic function on the torus, okay. Which means it is going to be holomorphic at the torus minus image of all these poles, and you see all these poles, if it has a pole at one point, because of periodicity it will have a pole at every translate of that point by the lattice, and all these will go down to a single point in the torus below, okay. So it will have, and you see therefore we get a meromorphic function, alright. And so and such a function is what is called an elliptic function, and we have our standard example is the Weierstrass Phe-function and its derivatives, alright. So take a general elliptic function, okay, and see I am trying to define what is meant by the order of such an elliptic function. So you see, so I make the following claim. So let me write this, number of times f assumes a value lambda in C. Look at the number of times the function assumes a value lambda in C. Now that will be equal to the number of zeros f minus the number of zeros of f minus lambda, okay. So the set of all z where f of z equal to lambda is precisely the set of all zeros of f of z minus lambda, okay. And the fact is that the number of zeros of f minus lambda, so you know, suppose I am looking at only number of times f assumes a certain value, and suppose I look at that only in a translate of this fundamental parallelogram, okay, in a translate such as OA BC. Of course I am sorry to call this also as O, because this is O and that is 0, so let it not confuse, okay. So this is the origin and this is it's bad notation. So you see, you take a translated parallelogram like this, okay, and I am considering I am confining my attention only to number of values, number of places inside this parallelogram where the function is taking the value lambda, okay. So let me write that. So I'm not trying to write that because it will be too much to write down, but let me again repeat, when I say number of times f assumes a value, I am looking at only values inside a translate of the period parallelogram, this basic parallelogram, okay. So that I translate it so that the edges of the parallelogram don't hit any poles, I mean that's all I want, I do not want the edges of the parallelogram to hit any poles of this function, okay, and I look at the number of times f assumes that value, then this will be equal to the number of zeros of f minus lambda, okay. But you see we have just, but you see f minus lambda is I claim that this is number of poles also of f minus lambda, okay. That is because you see the number of zeros minus number of poles will be integrating f minus lambda derivative by f minus lambda, okay, which continues to be doubly periodic, okay. So again I am using the argument principle, alright. So the number of zeros of f minus lambda will be equal to the number of poles of this will be equal to the number of poles of f minus lambda, and you see translation is not going to affect a pole, okay. Then the number of poles of f minus lambda, I mean these are the points where f is going to infinity, and if f is going to infinity then f minus any constant complex number will also go to infinity. So this is also going to be equal to number of poles of f, okay. So the moral of the story, and mind you, and this is exactly number of times f assumes the value infinity, okay. The number of times at a pole f assumes value infinity. So what this calculation tells you, okay. So of course at this point I am using argument principle, okay, literally replacing the numerator by f minus lambda derivative and put here f minus lambda, okay. So so what have I proved? I proved that an elliptic function, okay, will assume each complex value including the value infinity exactly the same number of times. It cannot assume one value many more times than it assumes another value, okay, and this number is called the order of the elliptic function, okay. This is equal to order of the elliptic function. This is the order of the elliptic function f, alright. So we have examples of this. So you see, so the examples that we have seen are, you know, phi, so you see zeta, so phi of z is order 2, well, and its derivative is order 3 and so on, alright. So now you see, now this is enough to prove my claim. See, because if E1 is equal to E2, then you are saying that this value, common value, which is E1 or E2, is assumed at half and at tau by 2, okay. But you see at half already it is assumed twice, okay, because you see at half it is already assumed twice, and at tau by 2 it is assumed twice, okay, because order is 2, it will assume each value twice, okay. So at half it will assume the value E1 twice, at tau by 2 it will assume the value E2 twice, okay. That is another way of saying that p tau of z minus E1 has a 0 of order 2 at half, p tau of z minus E2 has a 0 of order 2 at tau by 2. But if the E1 is equal to E2, what it will tell you is that it will assume that common value which is equal to E1 and E2 4 times. That is not possible because it is order 2, okay. So this is the argument that will imply the claim that none of the EIs are all distinct, okay, and this is extremely important, alright. So this implies the claim above. See, the point is that since f, see the elliptic function f, suppose so at least phi, okay, it assumes the value infinity twice because it has a pole of order 2, okay. So what will happen is that you will have the same, so it will assume each value twice, okay, it cannot assume a value 4 times, and the point is each value it assumes at a point with multiplicity 2, okay, it assumes each value at a given point with multiplicity 2, alright. So that is the reason why these three are all why the EIs are all distinct. Now what you do is now we really take advantage of the dependence on tau, okay. So we do the following thing, so let me use this side of the board. So you see what I am going to do is a I mean it's a very clever trick. So what you do is the following, so you again look at this carefully. E1 is p sub tau of half, okay, E1 is p sub tau of half, and what is it, let us expand it. This is well, I have to substitute z is equal to half, so p tau of z is 1 by z squared plus sigma omega in the lattice of defined by tau omega not equal to 0 1 by z minus omega the whole squared minus 1 by omega squared, okay, and I have to substitute z is equal to half. So if I do that, well, I will get 4 by z squared here, okay, plus, well, here what I will get is I will get let me rewrite it as sigma over m comma n an ordered pair of integers and m comma n not equal to 0 comma 0, and here I will get 1 by z is half, so it is half minus m minus n tau, because omega is supposed to be m plus n tau as m and n vary, that is how you get the lattice. And of course you do not include 0 here because the contribution for 0 is already out there, okay. Yeah, so it, sorry, I think there is no z here, so I put z equal to half, so I will simply get 4, yeah, I'll simply get 4, and yeah, that will just be 4, and then I will get minus 1 by, well, omega squared is going to be m plus n tau the whole square, okay, this is what I am going to get if I put z equal to half. Now look at it carefully, you will see that if you forget the lattice, okay, that is the reason why I wrote the summation over z cross v, okay, forget the lattice. Notice that this never vanishes, see, because purposely half is not a point of the lattice, and this of course converges, so you can see very clearly that in the upper half plane as tau varies, this is an analytic function, okay, this is an analytic function of tau on the upper half plane, okay. See, the clever thing is, so you see E1 depends on tau, E1 is E1 of tau, so if you want I should be careful and write E1 is equal to E1 of tau. Now look at it as a function of tau, it is very clear that this is an analytic function of tau, okay. In the same way you plug in for the other two roots, these other two zeros of the derivative of the phi function, so you will get E2 of tau and E3 of tau are also analytic functions of tau in the upper half plane, okay, alright, they are also analytic functions of tau. So by looking at the zeros of the derivative of the Weierstrass Phe-function, you have produced 3 analytic functions on the upper half plane, and now the trick is you define lambda of tau, okay, to be I think it is E1 E3 minus E2 by E1 minus E2, okay. So you define it as E3 of tau minus E2 of tau by E1 of tau minus E2 of tau, okay. You take this ratio. Notice that I told you for no value of tau these are all the same, okay. The upshot of that is E1 of tau will never be E2 of tau, so this will always be analytic. E3 of tau will never be E2 of tau for any given tau, so it is never going to be 0, alright. So what I am going to get, and you see E1 is not equal to E3, so this is never going to be 1, okay. So what I get is I get a analytic function on the upper half space, on the upper half plane, which is never 0, which is never 1, okay. And this is going to be the modular form that is going to first give you something that is not invariant under the whole unimodular group, but I will prove in the forthcoming lectures that that this will be invariant under the under a subgroup of PSL2C, okay, the congruence subgroup mod 2, alright. So let me write that down. So then lambda of tau is analytic on U on the upper half plane and is never equal to 0 or 1, okay. And why this function is so important is because you will see that if you compose this function with an automorphism of upper half space given by a unimodular matrix whose entries, if you read mod 2 you get the identity matrix, okay, then this function is invariant. So such usually functions which are analytic or meromorphic functions, holomorphic or meromorphic functions which are invariant under certain group of Mobius transformations, they are called automorphic functions or automorphic forms, and those which are invariant under the unimodular group PSL2Z, they are called modular forms. So, and this is a modular form which is not it is not a modular form for the whole unimodular group, but it is a modular form for only the congruence subgroup mod 2, namely those matrices in PSL2Z whose entries, if you read them mod 2, you get the identity matrix, 2 by 2 identity matrix, okay. So that is the importance of this function, and so this is how you see we cook up this is a partial invariant, okay, you can think of it as a partial invariant, and then use this to, so what we will do is we will use this to build a function which is invariant under the full modular group, and that is the function we are looking for, because we are trying to get hold of a analytic function on the upper half space which is invariant under the whole unimodular group PSL2Z. The first step is to get this modular form of weight 2, okay. So we will do that in the forthcoming lectures.